Hello, Math 200 students. We are on Chapter 5. So, Chapter 5 is about the normal distribution. Chapter 4, recall, was about the binomial, the geometric, and the Poisson distributions. Those three are more discrete distributions. So, like, I'm going to make this number of shots. And I'm either going to make 8 shots or 9 shots. Like, I can't make 8.47 shots. So that's why it's discrete. You're going to skip over numbers in your counting. The normal distribution is an example of a continuous distribution, where you can be any number and you won't skip numbers. Let's look at the normal distribution is a extremely common distribution in the real world. All kinds of things follow a normal distribution. It's the bell curve is what it is. All right, properties of a normal distribution. In section 4.1, you distinguish between discrete and continuous random variables and learn that a continuous random variable has an infinite number of possible values that can be represented by an interval on a number line. Its probability distribution is called a continuous probability distribution. In this chapter, you will study the most important continuous probability distribution in statistics, called the normal distribution. Normal distributions can be used to model many sets of measurements in nature, industry, and business. For instance, the systolic blood pressures of humans, the lifetimes of plasma televisions, and even housing costs are all normally distributed random variables. The normal distribution is a continuous probability distribution for a random variable x. The graph of a normal curve is called, the graph of a normal distribution is called the normal curve. A normal distribution has these properties. The mean, median, and mode are equal. So the mean would be this center line, the median would be this center line, and the mode would be this center line. The total area under the normal curve is equal to 1. That would be the case for any probability distribution. The total area under a curve or under that probability distribution curve would be equal to 1. The normal curve approaches but never touches the x-axis as it extends farther and farther away from the mean. So it's kind of common sense a little bit if you can understand that. So like whether it's a human's weight, average weight, or an average shoe size, or whatever it may be, more people are going to be gathered near the middle of that. So if let's say the average shoe size for a guy is let's say a 10 or 9.5 or something like that, I'm not sure, but somewhere around that, thereabouts. Well, the farther you get from that, the less percentage of people are going to be that. So like, if you get all the way out to like a size 18 shoe, that's going to be way out here, and there's going to be very few, very small percentage of men who have that size shoe. Or if you get way down here, like a size 4, there's going to be an extremely small amount of men that would have a size 4 shoe. And the closer you get to the middle, the greater percentage of men that would have that shoe size. All right. Between mu minus sigma and mu plus sigma, mu being the mean and sigma being the standard deviation, in the center of the curve, the graph curves downward. The graph curves upward to the left of mu minus sigma and to the right of mu plus sigma. The points at which the curve changes from curving upward to curving downward are called inflection points. So the graph is curving up. We would call this concave up. It's like a concave up is like a bowl that is right side up that holds water. It's a concave up bowl. But here is a concave down bowl, right? Between here and here. But where does it change? That's called a point of inflection. And the point of inflection would be right here, 1 standard deviation to the left of the mean. And then it's curving down. Concave down. Okay, it's an upside down bowl. But then right here, it's a right side up bowl again. Where does it change? Again, this is inflection point, and this is 1 standard deviation to the right of the mean. You have learned that a discrete probability distribution can be graphed with a histogram. For continuous probability distribution, you can use a probability density function, PDF. A probability density function has 2 requirements. 1, the total area under the curve is equal to 1, and 2, the function can never be negative. A normal curve with a mean mu and standard deviation sigma can be graphed using the normal probability density function And this is how you would form the graph of this line. I mean, this curve. This curve is formed by this equation, y equals 1 over sigma square root 2 pi times e to the negative x minus mu squared over 2 sigma squared. I want you to appreciate and be impressed by something about this thing, this equation. First of all, pi is in it. What in the world is pi doing in this equation? Pi is the ratio of the circumference of a circle to its diameter. Yet it shows up in just the most inconspicuous, unlikely places in the mathematical world. It just shows up, like here. It just shows up. What is it doing there? Another thing that shows up is e. E is the natural number. It's Euler's constant. It is 1 plus 1 over n raised to the n power as n approaches infinity. What is it doing there? And pi and e are together in one equation. And these two things that are so pervasive in the world, and there they are together, and they're together in the equation of the most common probability density function, the normal curve that like models almost everything, it seems like. Wow. Like that's something that gets into some philosophy, like some design to this whole existence, right? So anyway, I just think that's interesting, and a doctoral dissertation could be written on that. But anyway, moving on. A normal distribution can have any mean and any positive standard deviation. So the mean can be anything. It can be negative, could be positive, could be irrational, could be anything. But the standard deviation always is going to be positive because that's like the distance away, the standard amount of distance away from the mean. The two parameters, mu and sigma, mean, standard deviation, determine the shape of the normal curve. The mean gives the location of the line of symmetry, and the standard deviation describes how much the data are spread out. Okay, so here's the mean. The mean is at 3.5, and you have a standard deviation here of 1.5. This mean is also 3.5, but the standard deviation is smaller because it's all the data are gathered more toward the middle. Here they're more spread out. Here they're more brought in close. So the standard deviation you can see is less here. It's 0.7. Here the mean has been moved to the left. Now the mean of this one is 1.5, but you can kind of see that it's got the same amount of spread as the second one. And so the standard deviation here is still 0.7. All right, example 1. This is a good example here. Which normal curve has a greater mean? Which normal curve has a greater standard deviation? All right, normal curve A has the greater mean because the center of it is farther down the x-axis. It's farther to the right. The mean of distribution A would be around 15. The mean of distribution B would be somewhere around 12, or maybe a little less than 12. Which one has a greater standard deviation? Distribution B, curve B, has a greater standard deviation because the curve is more spread out. Curve A is tighter, so it's going to have less of a standard deviation. All right, I'd like to do this one. All right, which of these has the greatest mean out of A, B, and C? B, curve B has the greatest mean because the center of that curve, the mean of that curve, is farther down the x-axis. The mean of this curve is around 60. What about A and C? They have the same mean. Their means, the center of their curves are lined up in the same spot on the x-axis, somewhere around 45. All right, which one of these curves has the largest standard deviation? Curve C, because it's more spread out than A and B. Which one has the least standard deviation? Curve A, because it is the most tight curve. It's the skinniest. Everything's brought more toward the middle. So it has the least standard deviation. All right. Example 2. The scaled test scores for New York State grade 8 mathematics tests are normally distributed. The normal curve shown below represents this distribution. What is the mean test score? Estimate the standard deviation of this normal distribution. So the mean test score would be the center of this curve, which is right here. If I just kind of take my cursor down here, it looks like it's somewhere right in here. So let's see what that is. 650, 660, 670. So somewhere, if that's right, I might guess that to be 675. And if I look down here at the solution, that's right. The standard deviation, I want to, if 675 is the mean, I want to kind of estimate where this thing changes from being concave down to concave up, and that's going to be somewhere right in here. So somewhere right in here, what's that? That looks like about 650, maybe 640, somewhere in there. So if 675 is the mean, and the standard deviation goes all the way to one standard deviation below the mean would be somewhere around 640 or 650. I'm going to say that the standard deviation is around 25 or maybe 35, somewhere around 30. And if I look at the solution, they say that it's 35. So we weren't too bad off on our estimate there. I want to call your attention to this study tip in the margin over here. You can use technology to graph a normal curve. For instance, you can use the TI-84 Plus to graph the normal curve in example 2. So you do that. If you can see this command here, y1 equals, you do normal PDF, and then you do x, and then 675 for the mean and 35 for the standard deviation. Let's pull up our TI-84 and try to do that. Come on. Come on. There we go. So if we want to graph the normal curve, we went to y equals, so y1, we're going to go to distributions. So second, and then the bars button above it is the distributions. And then the very first option is normal PDF. The x value, we want that to be a variable. So we're going to let that be x. That's what's going to graph the curve instead of a single dot. The fact that it's a variable that changes. The x value could be way away from the mean or close to the mean or whatever. The mean in that example was 675. The standard deviation in that example was 35. And then we click paste, and then we can click graph. The reason this is so flat is because our window is nowhere near where it needs to be. We want it to center on the x-axis at 675. So let's let and the standard deviation is 35. Let's say we want to see around 600. And let's go to about, let's say, 750. That'll center it at 675. Let's let the x scale be our standard deviation, 35. Let's let the y min be 0. And the y max, the y max probably only needs to go up to, let's try 0.5. I'm not sure, but the y-axis is measuring our probabilities. And so our probabilities are always between 0 and 1. And usually the bars on the bar graphs don't even go above 0.5. That may even be too high, but I'm going to try it. Let's let the y scale be 0.1 and just see what happens. Okay, you can see it looks a little better, but the y scale is obviously too high. Let's let the y scale be something like 0.05 and see how if that makes it better. And let's let the y scale be 0.01. The scales don't matter. I just sometimes get a little obsessive about it. That looks a lot better. And we can make it go up even higher if we just make our y max be even lower. We can make our y max be 0.02. Try that one time. But that's looking like a normal curve now, isn't it? Looking good, looking good. Okay. Moving on to the next page. Standard normal distribution. There are the standard normal distribution. So what we just talked about was just a normal distribution. Now we're going to talk about what's called the standard normal distribution. The standard normal distribution has a mean of 0 and a standard deviation of 1. So the standard normal distribution, the center line would be 0 on the x-axis. And your standard deviation would be 1. So these things correspond to what's called z-scores. The horizontal scale of the graph of the standard normal distribution corresponds to z-scores. In 2.5, you learned that a z-score is a measure of position that indicates the number of standard deviations a value lies from the mean. So in the standard normal distribution, if your z-score is 1, that means you are 1 standard deviation above the mean. If your z-score is -2, it means you're 2 standard deviations below the mean. Recall that you can transform an x value to a z-score using this formula. Z equals x minus mu over sigma. X being whatever value you are, minus the mean of all the values, and then that thing is divided by the standard deviation. That gives you a z-score. When each data value of a normally distributed random variable x is transformed into a z-score, the result will be the standard normal distribution. So if you take any normal distribution and convert all of the scores in that normal distribution to z-scores, then you have now kind of transformed that normal distribution of whatever parameters it has, you have transformed that into a standard normal distribution. All right, so the standard normal curve is going to have the same area under it as the normal distribution that it was before it was transformed into the standard normal distribution, which is going to be 1. And also the values of these numbers here, -3, -2, those standard deviations and those z-scores are going to correspond to the empirical rule. The empirical rule is, 68% of the data will lie between within 1 standard deviation of the mean. So it'll lie between, in this case, -1 and 1. Then 95% of the data lie between -2 and 2, and so on and so forth, just like the empirical rule told us before. All right, the cumulative area is close to 0 for z-scores, close to z equals -3.49. The cumulative area increases as the z-score increases. The cumulative area for z equals 0 is 0.5. The cumulative area is close to 1 for z-scores, close to 3.49. So let me tell you what that means. So the cumulative area is like, if I'm at -1, the cumulative area would be all of the area from -infinity all the way to -1. So the area up to there would be all of the blue area to the left of -1. Notice if you're down here at -3, there's almost no cumulative area yet to the left of -3. There's a little bit, but not much. At -2, there's a little bit more, but still not a lot. -1, you start to get, some decent amount of area. At 0, what area do we have to the left of 0? Well, since the total area is 1, exactly half of that is to the left of 0, so it would be 0.5. All right, how much area do you have once you get to 3? All the cumulative area once you get to 3 is almost all of it, so almost 100% or almost 1. All right. We're not going to have to use the standard normal table that's in the back of the book because we have our calculator. We're going to use our calculator. If you want to use the standard normal table, go right ahead. I guess we can even show how to do it here. Find the cumulative area that corresponds to a z-score of 1.15. So you'd have to go down this z column to 1 and then go over to you have to go all the way down to 1.1 and then go to 0.05 because 1.1 and then 0.05 makes 1.15, and there's the total area for that z-score. Now what I would recommend you do is go to your calculator and you're going to go to second distributions, go to normal CDF, normal cumulative density function or cumulative distribution function. All right, the lower bound and the upper bound. If we wanted to do it for a z-score of 1.15, our lower bound would be negative infinity. All right, let me show you what I mean by that. Look at this picture. If you're looking for the cumulative area up to 1.15, then the leftmost value, that your left endpoint would be all the way at negative infinity. And then your right endpoint would be 1.15. Okay, so let me show you how to type that in the calculator. The lower is the left endpoint, the lowest you want to get to. You can't put in negative infinity, so you put in the lowest thing you can, and the lowest number you can put into the calculator is -1 times e to the 99th. That's the lowest thing the calculator can comprehend. So you say -1 e99. Let me show you how to type that in. -1, and then this is the exponential button to do scientific notation, like times 10 to the something. The double capital E right there. You click that, and that means times 10 to the, and you put 99. So that's -1 times 10 to the 99th. So that's a very large negative number. The upper bound, we're going to put 1.15. The mean for the standard normal distribution is 0. The sigma standard deviation for the standard normal distribution is 1. So we leave that at 0 and 1, and we click paste, and that will tell us the answer, 0.8749. All right. Is there a part B to this? Find the cumulative area that corresponds to a z-score of -0.24. All right, that shouldn't be hard to do. Now that we've done the first one, the second one, the lower limit still going to be -1 e99. The upper limit is going to be -0.24. That means we're 0.24 standard deviations below the mean. So we're finding the area that corresponds to that. 0.405, 0.4052 if you want to go all the way to that. Now let me give you kind of a concept of what this area is telling us. This last answer we just got tells me that about 41% of the data will be less than -0.24, or will be less than 0.24 standard deviations below the mean. The answer we got up here, the 0.8749, means that about 87% of the data will be less than 1.15 standard deviations above the mean, or will be less than a z-score of 1.15. Okay. You can use the following guidelines to find various types of areas under the standard normal curve. Sketch the standard normal curve and shade the appropriate area under the curve. Find the area by following the directions for each case shown. To find the area to the left of z, find the area that corresponds to z in the standard normal table. All right, so that's exactly, well, we don't have to use normal table, we can just use our calculator. That's exactly what we just did. To find the area to the right of z, what we would do, I'll show you what we'll do in our calculator. Let's find some good examples. Again, this is going to be way easier in the calculator. Find the area under the standard normal curve to the left of z equals negative 0.99. That's exactly what we just did. There's no difference in what we've already done. So I won't even do that one. I won't even bother to do that one. That's just the same thing. But this one's going to be a little different. Find the area under the standard normal curve to the right of 1.06. Okay, this one's a little different. Again, second distribution, option 2, normal CDF. This time I'm finding the area to the right of 1.06. So what's my lowest value in this area? The lower value, the lower bound, is 1.06. What's the highest value in this area? Well, it goes all the way to infinity. So the lower bound in this case is 1.06. And the upper bound is going to be infinity, or I'm just going to type in positive 1 E99. Notice for negative infinity, I had to type negative 1 E99, but for positive infinity, I'm just typing 1 E99. Okay. Mean and standard deviation are still what they are, 0 and 1, and it tells me the answer. So the percentage of the data that are above 1.06 is 0.1446. All right, here's another good one. If you'll ever get to it. Again, a little different. Find the area under the standard normal curve between, so not below something, not above something, but between two things. Between negative 1.5 and 1.25. Using a table, this would be a lot more complicated, but using the calculator is not complicated at all. All we have to do is the same process. This time the lower bound is negative 1.5. Negative 1.5. And the upper bound is 1.25, just like it told us. Mean and standard deviation are still 0 and 1 because we're still dealing with a standard normal distribution, and we get that about 83% of the data are between negative 1.5 and 1.25 z-scores. So 0.8275 if we want to get all of that in there. All right, and that is the end. Let me see if there's anything important in this part before I close it out. Yeah, there's one more thing to say, although I think you already know this, but values lying more than 2 standard deviations from the mean are considered unusual. So a z-score of more than 2 or less than negative 2 is considered unusual. Values more than 3 standard deviations from the mean are considered very unusual. So a z-score greater than 3 or less than negative 3 is considered very unusual. And that should be enough for section 5.1. Good luck on that assignment. I'll see you again in 5.2.